Hi, in this video we will continue the factoring and completing the square technique. Let's start with the factoring. In example 1, you have a quadratic polynomial function which is equal to 0. So for this case, we want to simplify the x squared term into x plus a, where a is the constant, multiply x plus b. Right? So we want to find the ab for this constant. What will be the number? So if we're able to achieve this, this is called the factoring. So the easiest way to find the a and b in this case is to use the calculator. So you can easily find the root for this case is x equal to 1 and negative 5. To check this root, you can substitute, okay, 1 square, 1, then 4 multiply 1, you get 4 here. So total 5 minus 5. So we prove that this is the root. Negative 5, you substitute, you should get 0 as well. So since that your x is 1 and negative 5 in this case, so therefore your a must be negative 1, so that in total you can get 0, multiply the term here which is equal to 0. And your b in this case must be plus 5, right? So that when you product it, it will be equal to 0. So we can rewrite this into x plus negative 1, or directly you write x minus 1 here, and on the right hand side is x plus 5, where your a is negative 1, b is 5. So after factor you should get this. In this case we can say that the polynomial function for x squared plus 4x minus 5 is reducible. Why? Because it can be further factorized into the linear factor like this, right? So in this case, we get more simple factor here. From power of 2, which is the quadratic, so this is quadratic polynomial, to x to the power of 1, which is called linear polynomial. So if we want to further reduce this to x to the power of 0, can we do that? If all of you know that we cannot further factorize this, so in this case we are saying that the linear factor is the most simplest form, where we cannot reduce it further or we cannot factorize it further. Let's continue with the example 2. In this example, x squared plus 4, you are checking whether you can use the factorize to further reduce it into this format. So in this case, you can see that by checking the calculator, you get the x equal to 2i. So since this is complex number, we cannot apply into this formula because a and b must be real number. So we say that x squared plus 4 cannot be further reduced anymore, or cannot be further factorized. So we can say that x squared plus 4, this polynomial, is in the most simplest form and it cannot be further factorized. In general, we call the quadratic polynomial for this example because you can see that the polynomial has degree power of 2, and we call it as linear polynomial if the polynomial has degree power of 1 here. So you can separate it into reducible and also the irreducible case. And I have shown you that if the root is a real number, like this case, the root is x equal to 2 here and x equal to negative 2 here. So for this case, we can further reduce the x squared minus 4 into x minus 2 multiplied with the x plus 2 by using the factorization. For the second case, it's also possible that you get the repeated real root, where in this case, your x is equal to 1. Since it's a power of 2, means that you have repeated root, which can be written in this form. So x minus 1 multiplied with x minus 1. So in simple, you can provide it into x minus 1 power of 2. For the case 3, if there is no real root, or what we say the complex root, for example in this case, you check the calculator, you get the root x equal to 2i. To confirm this root, we substitute 2i to the power of 2, we get negative 4. So negative 4 plus 4, we get 0. So 2i is the real root. So in this case, we say that we cannot further factorize it. And also we cannot further reduce this into linear factor, right? This is extra information also for you guys to check whether we can reduce the polynomial into linear factor or not. So for the first case and second case, you can see that if b squared minus 4ac greater or equal to 0, then we can further reduce it. And for the second case, if the b squared minus 4ac less than 0, then it cannot be factorized. To further improve your understanding, please check this figure, where this is for case 1, that you have a polynomial function x squared minus 4. By using calculator, you should be able to obtain your root x equal to negative 2 and 2 here. Therefore, we can form the linear factor x minus 2 multiplied with x plus 2. In this case, the root will always cross the x-axis here. So these 2 points is our root. So for the second case, if you plot this function, you get a curve like this. And if you check the calculator, you found that the root, it will be x equal to 1 here. So this is the root. Therefore, we can say that the factor is x minus 1, okay, twice. So this is repeated linear factor. And there are 2 repeated real roots. And this can be further simplified into x minus 1 squared. For the last case, if you have polynomial function like this, x squared plus 4, we cannot further factorize it anymore. If you use calculator, you get the root to be a complex form, where you have imaginary number. So for this case is 2i. So where is 2i? So I is in your y-axis here. So 2 will be somewhere here. So this is your root, 2i. So this is your real axis. So you see there is no curve crossing this. So there is no real root. Therefore, in this case, we cannot factorize the polynomial function. So far, our factorization technique is only useful for the polynomial function of degree 3 and below. We have a polynomial function of degree 3 in this example. So let's say you want to factorize this. First thing, you can use your calculator to find the root. So in this case, your root will be x equal to negative 1, 5i, and negative 5i. So you see there are 2 complex number and 1 real number here. To check if the root is correct, you can substitute the value inside. Let's say negative 1, you substitute, you get this, okay, plus 1 minus 25 plus 25. So for root, when you substitute, you should get the function equal to 0. So you can verify this by using this approach. So once we get the root, so these are the three roots, so we can directly write the answer into this format. Please take note that the factor here must not be in complex form. So therefore, multiply it to get the quadratic form. Right? So in linear factor, this value shouldn't be complex number. So we have to convert this into quadratic format. So you perform it, you should get the final answer to be this. So I might multiply I, you get negative 1, negative become positive here, right? So negative 5i multiply x plus 5i multiply x, you get 0 in the middle. So after you factorize this function, the final answer should be equal to x plus 1 multiplied with x squared plus 25. So we can use calculator and you can easily find the answer, right? So let's look at if we want to factorize the function with x to the power 4 and above. So these are the possible answer. So for polynomial with degree of 4, so you might have linear factor. So linear factor, so you can see that all of them are different. Or you have a repeated linear factor, where you can see the linear factor here, 2x plus 1 is repeated in power of 2. And not only the linear factor, you may also have quadratic factor. For example, this is linear factor, right? Linear, I put L here. So repeated linear factor, so repeated R, right? So this is linear factor, and this one is quadratic factor Q. Right? And last case is possible also you get the repeated quadratic factor. Like for this case, this x squared plus x plus 2 here cannot reduce further. If you reduce further, you will get complex number, right? So this is our quadratic, okay, repeated quadratic. Okay, to solve the polynomial function of degree 4 and above, so for the first step, you have to find out what is the possible linear factor. So we look at the last constant here, 4. So choose the root, okay, the factor, linear factor from this constant. So there are many possibilities here. Your root may be, so this is the root. So for the first factor, if you choose x plus 1, then you get the root x equal to minus 1. To check if this root is correct, then you have to substitute inside this function. Okay, let's say we substitute. Oh, 4 you get 1 here, minus with 5, negative 1, I get power of 2, I get 1 here, plus 4. So 1 minus 5 plus 4, you get 0, which means that this is one of the positive, this is the actual linear factor for this function. So we have to choose the root that make the polynomial function 0. So for example, in this case, I show you that we choose the root x plus 1 to be the linear factor because this is the real root which make the function to be 0. So we can say that x plus 1 is the actual factor for the function. And you can try with other, if let's say you start with this function, okay, saying that this function can be factorized by this linear factor. So you substitute the root x equal to 4 inside, and in this case, you will find out is not equal to 0. Therefore, this is not the actual linear factor for this function. So don't proceed with this, right? So with that, we proceed with this actual linear factor. So in step 2, we proceed with the actual linear factor x plus 1. We have to perform the long division. So long division is also same with the factor here. Just that the format is in long division, where we put the function, okay, inside here, and then the linear factor that we select, we put it here, and you start to divide. So firstly, x plus 1, you have to multiply x to the power of 3 here, right? So this one multiply this, you get this answer. This function here minus with this, you get this function. So you have negative x3, so you have to multiply with negative x squared here. So you proceed, continue this approach, and you will get the remainder to be 0. So it indicates that you obtain the correct factor. If you get something not equal to 0 here, then means that this linear factor is not correct. So for example, if you put x minus 4, you continue, you shouldn't get this equal to 0. Right? So in this case, you know that this factor is not correct. And you have to move and find a correct one with remainder equal to 0, like this case. So from here, basically what you are doing is you take the x power of 4 minus 5x squared plus 4. And then you divide it by the linear factor x plus 1. Then what you get is x to the power of 3 minus x squared minus 4x plus 4, right? So we can rearrange this to obtain this. So the linear factor that you have here is x plus 1, and you have a quadratic factor here. So what you need to do next, you have to further factorize this x power of 3 term. So we continue with the x power of 3 term here. So if you have polynomial function with the degree 3 and below, then you can use the previous method, right? Which is by using the calculator, we can find the root. So the root for this function is 1, negative 2, and 2. So all of them are real number. So we can write the linear factor in this way. So lastly, you want to find x power 4 minus 5x squared plus 4. So after you factorize it, you get this answer. By using this method, basically you can solve these 3 cases where you have the linear factor. However, for the last cases, you can see you don't have linear factor. So you have to use the quadratic factor step to solve this. Let's continue with this example. So we want to factorize this function. So same approach, we look at the last constant, and then these are the possible linear factor. So we try the linear factor, the root 1 by 1, negative 1, we substitute inside this function. We get it not equal to 0. And then you continue with x equal to 1, you substitute, you get not equal to 0. And you continue until the last root, okay, you still get not equal to 0. This means that there are no linear factor in this case. So you have to proceed with the quadratic factor. So if there is no linear factor, so there is high possibility that there is quadratic factor. So the general formula for quadratic factor is ax squared plus bx plus c. You have to find out the constant a, b, c. So in this case, the a we assume to be 1, right? Because if you have the quadratic factor x squared here, so 1 multiply 1, you will get 1 here. And last term, 4. So 4, let's say this is a c, let's say I have a d function here. So c multiply d, you will get equal to 4. So there are many possibilities for this thing, right?
For example, your C can be -1, then your D will be 4, your C to be 1, your D to be -4, and so on. So there are many possibilities. Okay, so let's continue with this problem. So we assume that this function can be equal to quadratic factor because there is no linear factor. It cannot be represented by something like this: x plus a, x plus b, and so on, right? So we have proved that there is no root for this linear factor. So we have to proceed with the quadratic factor. So this is our assumption. We say that this function can be equal to this. And we continue, okay, you expand it, you get the term. We have to solve the unknown a, c, b, and d, right? So you can form the equation where 2 will be equal to a plus c, first equation. Second equation, 5 equal to this. Then your 4 will be equal to this. Lastly, your 4 here will be equal to BD. So as we mentioned before, for BD equal to 4 here, so in total for this case, there are 6 possibilities where your B and D, if they are integer. So first, your B -1, right? Your D is -4, you multiply, you get 4. So if your B is 1, your D is 4, you will still get 4. So these are all the possibilities. So let's say in this case, we choose your B equal to 2 and your D is equal to 2. And then you substitute inside and you solve the equation, and you should be able to find your A equal to 1, your C equal to 1. And these 4 values should be able to satisfy these 4 equations. If you choose other, let's say for this case, you choose the B equal to -1, D equal to -4, and then you solve the A and C, you substitute inside this equation, and it doesn't satisfy one of them, for example, then this is not the case, right? So you have to eliminate one by one. If you're lucky, you can get it, okay? So, or if you're lucky at first, you can directly get it, or if not, if you're unlucky, you have to solve all until the last case, only you can get it. So this is our suitable A, B, C, D to satisfy all these functions and equations. So once you solve it, you can substitute the equation, okay, A, B, C, D. Your A, B is 1 and 2, your C, D is 1 and 2. So after you substitute, you see that these two terms are the same, so it can be multiplied together to get square. So this is our repeated quadratic factor. With that, we have covered the factorization for the polynomial function of degree 4 and above. We should be able to find the factorization for linear factor, repeated linear factor, distinct quadratic factor, as well as repeated quadratic factor. So you should be able to solve it now. This is the formula for the completing the square. For example, if you have a polynomial function with degree of 2 here, so in this case, you can see that the general formula is ax squared plus bx plus c. You want to transform it into some function x plus a constant in the power of square. So if you have a constant a in front, you have to factor out, then you get this b over a x. So just factor out with respect to x only. Then you will want to convert this term inside the bracket here to x to the power of 2, right, plus c. So the constant here, you have to divide it by 2, so it becomes 2a. So for this term, let's say you expand it, what you get of 2. So when you expand, you get x squared, b over a, you get b over a squared. Sorry, this will be 2. So square, and at the middle you have b over a x, right? So therefore you have x squared plus b over ax. This is the additional part. Therefore you have to minus with this part, which is b over 2a squared. So with that you obtain this formula. Let's solve this problem. We want to get the completing the square for this function. So first step, you factor out the two constant. Okay, 2 multiply x squared, 2 multiply negative 6, you get back the negative 12. Then you apply the formula. So minus 6 here you have to divide by 2, right? By following this formula, 2 here. Then you have to minus with additional part. So for this part here, it's exactly the same with the part inside. So you have to minus the part here, which is exactly the same with 6 over 2. This one. So don't forget the power of 2 here. Then you can continue to solve this problem. 6 over 2 you get 3. 6 over 2 here you get 3. 3 multiply 2 you get 9. Then 2 multiply inside, you get this term. 2 multiply here, you get 2 here. So negative 9 remain. So these two constant, 18 minus with the 9, then you get negative 27. So this is our final answer. So let's try with more exercise here. So let's say you have this problem, you want to completing the square of this function. So first thing, we remove the constant where you have 1, so we don't need to do anything for this case. Next thing, we apply the formula. So we want to get something in the power of 2. So the x squared plus 5x here, 5 you have to divide it by 2 based on the formula. Then based on the formula, you have to minus with the part inside here, 5 over 2 power of 2. Right. Then you minus with 11. So 5 square, 12 square, you get 25 over 4. Then 11 is 4 over 44. So minus minus, in total you get 69, which is this answer. To check this answer is correct or not, you can expand it, right? X square plus multiply 2, you get 5x plus 5 square is 25, 2 square 4 minus with 69 over 4. So this term, if you calculate, it should be negative 11. So with that, we can check that your answer is correct in this case. Let's look at the second problem here. So you have 5x squared plus 9x plus 8, where you have a constant 5 in front. So take it out, 5. So x squared plus 9 over 5 here. So we stop until the term with x only. So 8 don't include. Right. So next thing, we continue, apply the formula. Then you have x 9 over 5 divided by 2. Okay, this one should be 10. X, okay, in bracket of power of 2. So this term inside you have to minus 9 over 10. Don't forget this whole thing must be power of 2 plus 8. Right. So this bracket, make sure you bracket it correctly. Then you multiply your 5 inside, you get this minus 9 power of 2. Okay, so 10 power of 2 you get 100. So minus multiply with 5 plus 8. So you calculate this, you should get the answer in 79 over 20. And then you get the same answer here. You should have learned the factoring as well as the completing the square. So when do we need to perform this in the integration? If you have an integration problem like this, so first of all, if you check, if you use the substitution method, if you differentiate below, you couldn't get relationship with the top part. So substitution is not recommended. Integration by part, you don't have two functions multiplied together, so it's not recommended as well. How about trigonometric substitution? You don't have something like a square plus b square here, so it's not recommended as well. Basic integration rule. So you see that all of these methods cannot be applied to solve this problem. So you can see that the technique that you have learned previously, like the substitution, trigonometric substitution, basic integration rule, and integration by part, cannot be used to solve this problem. So now you have learned the new technique, factoring and completing the square. Let's try to reduce this into a much simpler format. So in this case, you can see x to the power of 4, things like this, we can try to use the factoring. So by using the factoring that you have previously, okay, you should be able to factor it into a linear factor here and with a quadratic factor. So we can simplify this by equal to, okay, this form, where we can replace the term at the bottom to be this term. Once you convert it into a function in the multiplication of linear as well as the quadratic factor here, then you can apply a method so-called the partial fraction technique, where you can further simplify this into the corresponding linear and quadratic factor. Right? You can see x minus 1 is from here, it can be separated out, and just that you have to find out what is the unknown constant here. So in this case, if we perform the partial fraction technique, you should be able to find the constant here to be 1 over 12. So x plus 2 linear factor, so the constant that you should be able to find is 1 over 6. And lastly, for the quadratic factor, so in this case, you cannot further reduce because the root will be in complex form. So we have the quadratic function. So for quadratic function, at the top here, it should be in ax plus b format. So in this case, the constant b is 0, and you get the constant a to be negative 1 over 4. So you will learn this more in the partial fraction technique. So you can see that these two terms is in the 1 over x format. We can use the basic integration rule to directly integrate it, right? So you should get the answer in ln. And for this part, if you let the substitution x squared u equal to x squared plus x plus x plus 2, then you should be able to get 2x plus 1. But over here you get something in x, but you don't have a constant here. So what we can do is we can try to reduce this factor here, x squared plus x plus 2, reduce it further by using the completing the square, where you can see that after the completing the square, you get x plus 1 over 2 to the power of 2, okay, which is the square term, plus a constant 7 over 4. So you can continue to perform the substitution where you let u equal to this term, and then after you substitute everything, you should be able to get this form. So you can see that 2u over 4u squared plus 7, if you differentiate the bottom part, you get 8u, which is something relevant to this, right? So in this case, we can use the substitution to solve the left integral here. On the right integral, which is negative 1 over 4u squared plus 7, so for this case, you can see that if you use substitution, you will have remaining u at the top. So substitution is not suitable to solve it. So you continue, you look at the bottom part, it will be a squared plus b squared term. So we can use the u to be the trigonometric substitution. which is the A tangent, because it's a summation, A square plus B square. So A tangent angle. So we can use trigonometric substitution to solve this. And by doing that, you should be able to get the final answer. So in general, factoring is able to reduce a complicated polynomial into a much simpler form, which is in linear factor and quadratic factor only. And by doing this, by the partial fraction, you're able to separate it into much simpler form, right? However, for a quadratic case, quadratic factor, you have to use the completing the square to reduce it to linear factor format, like this one.